All right, so hope you guys are all doing well. We have for next class 3 people that are signed up to present, but I was hoping that we would get more people today. So here's the list of all of you in the class. Yeah, I think this is all of you, right? I didn't miss anybody. And for instance, Paul is presenting 6. He's actually working on this material, and this material is not in the book. So he'll be telling us about it, and then he's going to show us what research he's doing with it. Now he is going to talk about strongly correlated oxides, and actually that's in page 87 of the book. So the homework for everybody is to look at those materials that are going to be presented in the next class. Look at page 87 in the book. Look at page 95 in the book, and read them. Organic semiconductors. What is I'm assuming that you have that knowledge, and what the people that are presenting are going to do is give you some more on top of that. Or if you have questions about these things, you can bring them to that class. So if you have questions about strongly correlated oxides, Nahi is going to present about some of them. That's actually a really big topic with way too many things to know about them. So if you have questions, and if she doesn't know what you're asking about, that's okay, because she's not the expert on it. But she is going to be an expert for the day on one particular version of that topic, particular subject on it. You don't have to know everything, but if you have questions about it and I know the answer to it, I'll pipe in. If I don't know the answer to it, we can ask an expert about it to tell us about these things. So, Derek, you have a material you like? All right, pick one. And then you write it down here. Okay, nobody has replied as far as I can tell right here. So you just hit reply and then your name and what you want to do. Okay, Masur, you have one?
Yeah, but I need to contact you in email.
Okay. So yeah, just go with that. Ahmed, you said you were doing zinc oxide or something like that?
Yeah, I have gold pyramid.
The gold pyramids. Okay, and what is the material? What would we call them? Gold pyramids on, right there. That's silica. That's close enough. All right, so this is not in any book, as far as in our book or any book, because as far as I know, this was developed by the McElroy lab. So is it on papers already? I think it is, right?
There's guys Vietnamese working on this.
All right. So you think you can present in the next class?
Yes.
All right, perfect. So I need somebody else to pipe in for next class. Maybe you don't get to present. Cosmo, you're already signed up. You're doing
Yes, I saw that.
organic semiconductors. And this is the first presentation you're doing. You don't have, again, to do one on things that are on the book. Now there's 2 that are not in the book, 2 that are in the book. And then if you go over here, there's another one. Pick the technique you will present. So in this one, we had different, so we had different techniques. The class was bigger too. So as far as I know, we have a sputtering, right?
Yeah.
Casper wants to do sputtering. The other ones are not taken yet. And if you want to do something not on the book, not on this list, just clear it with me. Okay? So that's the technique you want to do. You said you wanted to do DFT.
Yes.
All right. And I don't know if anybody has something. I'm going to erase this table and put your table with your names. And you can start.
Depending
All right.
And I guess it's sort of a supplement to the.
And remember, you only get 10 minutes, so you don't have 2 hours to talk about the topic that you like. Yeah? AFM? Yeah. And then you just tell us what type of AFM you're using, because there's two. I believe the book covers both. Tapping mode versus height mode. So tapping mode is the one that is going like this. And then the other one is going like at a single height, and then it's measuring what is the deflection that is happening as you go over, but it's not the same thing. Kind of like you're driving it with a frequency and you're seeing how stiff it is the tapping mode. The one where you're not constant, but it's supposed to be kind of like a constant, and then it can go up and down. All right. So yeah, I can put you down for that. All right, any questions about this? Stop sharing. Yeah, that's on Thursday. Remember, it's a 10-minute presentation. I don't need you to give me a dissertation on it. You give me a dissertation on it, I'll fail you because you don't follow directions.
If I could get a first draft that done by tonight, would it be possible for me to bring that to you tomorrow morning to just sort of see if it's.
Yeah. And again, if you have too much stuff, I can tell you you have too much stuff. Another thing, I've been doing this for a couple of years. So I've seen people do what I consider failures. One person decided that they wanted to talk about superconductivity. They had no clue what superconductivity was, and they thought that they were just going to download a PowerPoint from a faculty member somewhere and present it to us. And it was obvious that he had no clue what superconductivity was, right? And even if you give credit to the person who gave the presentation, but you have no clue about what you're talking, then that's no use to us. So don't do that. The other person that was a failure, in my view, was somebody that wanted to talk about graphene, which is a huge topic again. Graphene was like the bomb when I was a young kid like you guys. And what he wanted to do was just impress us and throw all of this jargon and funky words at us. And it turns out that I was really annoyed by that, because not just because he was trying to say things that he didn't have a clue about, right? But because the class in that setting didn't call him up on his BS. So if you guys don't call somebody on their BS, I'll also be mad at you. Does that make sense? You guys know when somebody's trying to be like that, right? You guys would be able to tell. So call them out on that. It's not just expertise, right? Like if I started talking to you about the superconducting cosmological strings in the universe, you guys know that I'm BSing you because there's no such thing, right? And if somebody was doing that to you, even if it was called graphene and blah, 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 you would know that they're doing that to you. So you're free to say like, okay, can you explain superconductivity? Can you explain cosmology? Can you explain? And you'll see that they crumble, right? You're a physicist. You kind of know, all of you more or less. I mean, there's undergrads, there's grad students, but you kind of know the same physics. So you would know when somebody's trying to BS you. So don't let them BS you. Questions? All right, let's go back to Bragg diffraction. Sorry? Yeah, I'll tell you about writing in a bit. I want to finish Bragg diffraction, and then X-ray scattering and all of that stuff, and then the other major grading component for your class. And that way you can get started during spring break if you're not doing anything. All right, so Bragg diffraction. We have that light, or maybe something else like neutrons is coming in. It has a k value of ki, that's the wave vector, and it's going to scatter off the planes. So now we have that they're not scattering off just the single atoms like we were thinking that they could do, In fact, for the single atoms, that's what they do with the people that do with determination of the structure of proteins or things like that. For condensed matter systems, for crystals, what we notice is that these planes are the ones that are giving you the scattering. And there's particular angles where the incoming radiation hits the plane in the right direction, and then it goes in another direction. And that particular plane is the one scattering things. So we knew that there's a Q value. And remember, Q is given in this case is this one minus this one. So this blue vector right here. And this blue vector is just exaggerated. It's supposed to be in the same direction as the plane so that you get a constructive interference. So what we have for any structure, we have that if this condition is fulfilled, you get constructive interference. But now you have that there's constructive interference and you have a static structure factor for the crystal. But you also have that the intensity of that scattering is dependent on different things. So we have that the intensity is given to us, the scatter intensity is given to us by the square of the scatter radiation, the total scatter radiation. So we have this guy that we calculated that we know that is coming to us at a Q that is equal to one of the planes. We know that there's so many cells in the system. And then we have the electromagnetic amplitude of the wave coming at us. So this guy is a number, positive. This guy is a number. It's a square, so it's also positive. This one is, we know that now because Q is selected as G, it's also a positive quantity and it's the static structure factor. But then we have that each of the cells has different position of the atoms, and we go back to this one because this is the only part here that could give us 0, so that even though we're in the right angle and the right Q, this guy could be 0, and we now have that the reflection is not occurring. So in this case, for instance, if we have cesium chloride, we see the 110, but we don't see a 100. Here in sodium chloride, we see the 200, but we don't see a 100. Why not? So that's what we're going to be answering now. Any questions so far? So this is from the previous class. So if you have questions, anything that looks funny or looked funny back then and you haven't processed yet, ask me now. No? We're good to go? All right. So let's start with this part, the missing reflection. So we know that the intensity depends on different things. And one of them is the specific arrangement of the atoms in the cell. So intensity depends on the arrangement of the atoms in the cell. This is one of your unit cells. And the dependence is given to us by this quantity, F cell, that depends on the angle that you have. In this case, one of our angles is going to be given by this, by some of the possible vectors that we have from each of the planes. And the HKL are those integers that go there. And now what we want to do is let's look at cesium chloride. So cesium chloride is a salt. It's a simple cubic structure. So this is the simple cubic structure is just SC. And what we know is that we're gonna have the Cl atom is at 0, 0, 0 in this unit cell. So we have the did I say cesium or chloride? Yeah, it should be the chloride atom. We assume that that one has a location 0, 0, 0 in our cubic. And then it has atomic factor that is given by, so this is the atomic, this is the cell factor, and it's composed of all of the elements in the cell. So for this chloride, we're gonna have 1, and this one also depends on this HKL vector. So this is the one that, and I think I didn't bring that previous thing, but we had a system, and this was the Q vector, and it was looking like this. You guys remember? That was the atomic for each of the atoms as a function of Q. So those guys depend on how big the atom is. It depends on whether it's on the C number of protons in the system. So we have one for chloride, and then that's how it scatters this chlorine atom. And then the cesium atom is at 1/2, 1/2, 1/2. So this would be our unit cell. So let me kind of draw it. So we have one guy in this corner, and then one guy right here in the center, right? And what that means is that there's actually other ones here, here, here. In all of the corners, there's one back there too. And then this red one gets repeated in this direction, this direction, this direction. So to get from the red ones, so the blue ones, all of the blue ones correspond to a vector that goes as H, A1, L, K, A2, and then L, A3, where these guys are integers. And then all of the red ones correspond to H, A1 over 2, K, A2 over 2, and then L, A3 over 2. So if I want to go to the next Unix cell, so this would be 1, 1, 1 is this guy. And then if I want to go to the next one, I would put 2, 1, 1. And then I go in this direction, right? And so forth. So the red ones are given by something. The blue ones are given by something else. The cesium atom is located there for that particular unit cell. And the form factor for cesium is whatever this guy is. So again, if we look over there, maybe chloride is this one, And cesium, because it's way heavier, is this one. You don't, and then as you go across like this, you're changing the Q parameter. You would be picking up some of those planes, but you see that there's a difference between the two, but it doesn't really matter. It's just like numbers, right? Those things are numbers that go into the equation, and they're all positive. So what we do then is that this cell is seen as a particle that is composed of these two guys, the two atoms in my unit cell. So the cell is scattering for a particular value, and then what we need to figure out is what that value is. So the one for the cell, and this cell is the cesium chloride one, is going to be given by summing over the atoms in the cell with their atomic form factors, the value of those, this and this for each of them, of those constants that go there, and then e to the negative I, this vector G, H, K, L, dotted with Ri. So there's atoms in there. We're gonna do one for the chlorine, one for the cesium. So this would be two atoms, and then you have the same G vector. And then this is the position, whether it's 0, 0, 0, or 1 half, 1 half, 1 half. So that's the summation for the cell. Any questions? So these positions are given here for that unit cell. That's what we stick in there. All right, so then let me look at that equation. So we have it here for the cell at some particular HKL. I haven't decided which one yet. Let's keep it open. So I have atoms that go there. There's two of them. I'm gonna stick that constant Fi. And then we're gonna do the exponential. And we have negative I. That's the imaginary number. Then this vector, HB1, KB2 plus LB3, and it gets dotted with this vector. So some integer xi a1. So this depends on the atom, right? Yi a2, and then ci a3. So I cross this vector with, I dot this vector into this vector, like that. And then I close the exponential. Questions? No? So then let's go back, and we see that one of the positions is 0, 0, 0, so it would be 0, 0, 0, whereas the other one is 1 half, 1 half, 1 half, 1 half, 1 half, 1 half. So if I do that, I'm gonna do first the chlorine. So I have the structure factor for chlorine at a particular HKL vector. And then, because this one was 0, 0, 0, I'm gonna have this e to the negative 0. So that's just 1. So I just get this guy by itself. Make sense? So what's the other one? We do the cesium right here. Again, in this Q vector. And now I have e to the And then I have the HKL, and then B1 dotted with A1 divided by 2. So if I do B1 dotted with A1, what do I get? You guys remember? Two pi, right? So I'm gonna be doing here exponential of I, and then when I do this one, H dotted with Xi is half, right? So I'm gonna have H over 2 pi, right? Plus, and then the same thing, K and 1/2, and then 2 pi. So I get K pi, and then the last one, L pi. Questions? So if we rewrite it, the cell for the G value HKL, cesium chloride, we get the chloride structure factor, which is at 0, 0, 0. And then we get the cesium structure factor at HKL, E to the negative I pi, not I pi, not H. Let me do it like this, exponential, I pi, and then in this case is H plus K plus L. All right, so now we just look at this, I pi HKL, and let's say we stick let us use some planes for this. So your favorite plane, the 1, 0, 0. You all agree that's your favorite? The easiest one to see, right? If we stick that one in there, what do we get? For cesium chloride. So we get F of Cl. I'm not gonna write the rest. F of Cs. And then this guy is gonna be E to the I pi. Did I forget the negative? Yeah, I forgot a negative here. What is E to the I pi? Sorry? -1. And this guy is a number, and it's minus this other number. Yeah?
Shouldn't the FCL and FCS be in a separate bracket from the exponent terms? Or,
So this guy has an exponent e to the 0. This guy goes with e to the 0, which is just 1. And this one is going to go to e to the negative I pi. So yeah, this is just applying to this guy, right?
oh, it's only to
Yep, because this one already has 0, 0, 0. So there's no e to the 0 right here is 1. So if you look at the imaginary plane, right? So this is the complex plane. We have 1 right here. We have -1 here. We have I here. We have negative I here. If we look at this guy right here, the here, and we get -1. So the pi here tell us that we're going from here in this direction and get here. So you see that this gives you a -1. Yeah, you could also do that. Yeah, exactly. Oh, -I, here's a I. Yeah, I forgot the negative here. Here's a negative. Negative, I forgot the negative here, and I stuck this negative here because I realized I forgot the negative. So if we look at that plane, we get FCL minus FCS. And now we have that the structure factor that we're getting, and let's say it was at this value, this is our G. I don't remember if this is the right place to put it, but let's say this was it, 1, 0, 0. We're gonna get this one and this one to subtract each other. So we got the difference of those structure factors versus another one where these two guys get added together. So in some places they add together, in some places they subtract each other. So we're getting a difference for the 1, 0, 0, and it would be the same for the 1, for the 0, 1, 0, and the 0, 0, 1, right? This wouldn't change. So 1, 0, 0 gives you this. Questions? That's the math behind it. Questions at this point? No? Make sense? Or not really? You guys have to speak up or not. Otherwise, I keep going. All right, from the math point of view, it makes sense. So now, let's talk about the 1, 0, 0 planes. So let's say that we were looking at this guy, right? So the 1, 0, 0 planes of this guy. So we have two colors for our atoms. And basically, if I were to look at it straight on, I would have atom here, here, here. Let's say I had this. These guys are my chloride atoms. And then I'm gonna have my cesium atom is right on the center. Okay? So red is equal to cesium atom. So my planes, my 1, 0, 0 plane, let's say is this one, like that. So those are my 1, 0, 0 planes. Make sense? So it's just going in that direction, right? So this direction, this is the 1, 0, 0 plane. All right. So if we're looking at one of them, this guy is contributing in this direction, right? This one is also contributing in this direction. So there's radiation coming in this direction, and then it gets scattered from that atom. And all of these guys are contributing in that direction. And there's 4 of them in this little unit cell. There's 8 of them. So let's assume that I'm taking all the ones that are in that little unit cell. There's 8 of them, but we're seeing the first 4. So we basically have that there's 4 of them, and we had this one and the one behind it, this one and the one behind it. Each of them is contributing 1/4 FCl. Now, this guy here is also contributing. And it goes in that direction too. Well, it's supposed to be the same one as my previous one. And this one is contributing FCS e to the I pi. So you see these 4 guys or 8 guys in the little unit cell are each contributing one FCl, and then this guy is contributing in the opposite direction, a complete FCS. So that's why those two guys cancel out, because this one is e to the I pi. Yeah? Cosmo, you had a question?
Yeah, I was you mentioned that the geometry of this crystal is supposed to be a simple cubic
Right.
structure. Yeah, it looks like from the diagram that you drew, it's almost exhibiting what I want to say is a centered body.
No.
Sort of,
Good question. What we have is a face center cubic. This is the face center cube. No, sorry. If all of these guys, if all of them were chlorine and this guy was in the center, then this would be a body center cubic. But what we have is that this is my unit cell. So there's 4 atoms here. Each of them contributes 1/4 to this guy. They're located at 0, 0, 1, 0, well, 0, 0, 1, 0, 0, 1, and 1, 1. And then this guy is the basis. So the basis is the decoration that is another atom. So if this guy was also chlorine, then we would have a body center cubic, but it's not. It's a different atom. So this is the unit cell is a cube, simple cube, with this guy in the 0, 0, 0 position. So each of the points of the lattice has one of the blue atoms, and then the red ones are the bases. Or you could say that both chlorine and cesium are bases, except one is located at 0, 0, 0, and the other one is at half, half, half.
So, is this sort of built off of the sort of the Wigner size cell representation?
So the cell would be exactly, yeah, the Wigner size would be for the chlorine atom. Yeah. All right, so we have the 1, 0, 0. Let's go back and do the math for the 1, 1, 0. And it's exactly the same as before, right? Well, you have any questions about this so far? We're all good? So let me just make sure that this part is clear. Because this cesium atom is halfway between the planes, right? The waves that is reflecting is just half the optical length. So whereas this one and this ones are separated by this whole plane, that means that the optical path that this guy and this guy take have the same length, plus minus, so that it's another wavelength, and it looks, all of them are positive, interfering with each other constructively. This guy is halfway there in between the two planes. So this optical path that this one takes differs from this one and this one and this one, so they were all the same in phase with each other. This one is completely out of phase because it's half a wavelength behind. So that's how they cancel out. Does that make sense now? All right, so now let's look at something where we have a 1, 1, 0. So doing the same math, right? I'm gonna have that this one is the cell at a G vector 1, 1, 0 for cesium chloride. And I get the same thing, right? There's an FCl, e to the 0, which is 1, plus, and now I would have to do this guy, the cesium, and then is exponential of negative I pi. And then if we look back at this formula right here, I pi, and then it's H plus K plus L. So I would have 1 plus 1 plus 0. So that gives me 2. So if we compare that one for this one to this one to this one, what we have then is that we get FCl plus, and then is e to the negative I pi to negative 2 pi I. So that means that it's just adding as 1, right? Because he goes the full circle. So now we get this. And that's the FC. That's the, both of them are now contributing positive. And what happened then is that you're summing these two guys to get a bigger value. So in this case, let's look at the same drawing as before. Before I gave you 4, so let me put it here. So we had these guys that were separate from each other, about the same length. There's the cubic lattice for the chlorine. I also have the cesiums right here. And let me put a couple more cesiums because so you can see these planes popping together. And then the plane that I want is not the 1, 0, 0. No, sorry, it's not the 1, 0, 0 or the 0, 1, 0, but rather the 1, 1, 0. So the planes now go like this. So that's one of my planes. That's another one of my planes. That's another one of my planes, and so forth. If we look at the unit cell, just one single unit cell, this is my single unit cell right here. And if we look at the contribution from each of the guys in the unit cell, this is the vector perpendicular to that, the plane perpendicular to the plane. We're going to have incoming radiation in this direction, and we actually have outgoing radiation in this direction for this angle. And then for this one, it's also like that. You okay, Cosmo? All right, so we look at this one, we see that each of these guys is contributing. This one right here, I could write down as 1/4 FCl, and all of the other blue ones in our unit cell. And this one is just the FCS. So big difference, right? In this one, they're out of phase above. This one down here, the red atoms and the blue atoms are in the same plane. And because they're in the same plane, the reflected here and the reflected here go together and have the same path, optical path, when they reach our detector. Questions?
Actually, yes. What would be the physical significance for this in terms of the study of the lattice structure for this fluoride ion?
Right, so now we know how for a particular structure, this is a simple cubic with a basis that is like this one, where one of the atoms is located at the center, the other flavor of the atom, right? So now we know that the possibilities, right? And here we have the planes. So I just did the 1, 0, 0 and the 1, 1, 0. Now we know that the 1, 0, 0, the 0, 1, 0, and the 0, 0, 1, they all disappear. Because it's 1 minus 1, 1 minus 1, 1 minus 1. We also know that the 1, 1, 0, the 0, 1, 0, and the 0, 1, 1 are going to be adding constructively. Make sense? And you have 1 plus 1, 1 plus 1, 1 plus 1. So at this point, what you can look at is, if you did not just coming back to this equation right here, HKL, which ones are going to give you interference that is constructive, and which ones is going to be interference that is destructive?
Would be if HKL kind of be an odd number or an even number, correct?
Exactly. So above we have odds, below we had evens. So if you have 2, 2, you should see it. 222, you should see it. 111, would you see it? Exactly. You wouldn't see it. So that tells us that we have odds. When we sum the indices and so if we sum the index, if they're odd, we get destructive interference. And if they are even, we get constructive interference. So based on those values, now we know, and I did this, it was a cartoon version of it. Let me see. Previous notes, previous class. I made this cartoon here. And you see that those big ones that appear is the 110, the 220, the 211, and the 310. And because it's cubic, right? It's a cube. There's no difference between the 110 and the 011 and the 101. They're all bunched here. By symmetry, they're exactly the same thing. So we get to see that 1 plus 1 gives you 2, 2 plus 1 plus 1 gives you 4, 2 plus 2 gives you 4, 3 plus 1 gives you 4. Those are the things that survive. In this case, these are the planes that survive. Now, the second thing that you ask, Cosmo, what does this mean for the experiment, is that we can look at this equation right here. So this is a number. It depends on what? Cosmo? What does this number depend on?
Space one, it depends on the space in between those.
No, 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 no. This number, lambda.
That would be the incident wave.
Yeah, the X-ray energy, right?
Right.
Right. So this is a number, depends on the system that you're using. It could be copper, K alpha transition. This right here, HKL, tells you different values for the planes. And it's actually, there's my picture over here, this distance, right, between these two planes. So for instance, this distance right here for the 100 plane, and this is the distance. So this distance is whatever, A. And this number right here, between this distance right here is A over square root of 2, right? So that's what that number is. And then the sine theta gives you the theta, which is this direction. So the plane that you're interested in goes in here. And then this angle is related to this angle right here is here in the equation. So we have the sine theta that goes there. So we get a lot of information from here to describe the structure that we have. We have whether the planes are going to appear. In this case, because this is a cubic structure with this basis, we don't see 1, 0, 0 or any of the odd planes. We also see that these guys appear here. And given the number here, we could stick it here. We know this number, we know this number, we would be able to tell what this is. And that would be related to the value of the unit cell, the length of the unit cell. So A is easy to extract from this data. So when we have that they're all in the same plane, all of these guys are in the same plane, they're doing the maximal interference, right? Because we're summing those two form factors and we get this bigger interference. Some of the reflections that we see in simple cubic structures are not going to appear in the body center cubic or the face center cubic. And that's the reason for this, right? So let me give you an example for the BCC lattice. Sorry, not BCC. Yeah, BCC lattice. That's the one I'm going to do. So this is the body center cubic. So for this unit cell, has two important points. The first one is at 0, 0, 0. And the other one is located at 1/2 A1 no, sorry. It's not, they're not XYZ anymore. The unit cell is A1 divided by 2, A2 divided by 2, and A3 divided by 2. So you could have, in the one that we just did, we had a basis, right? We had a cubic cell. The cubic cell, just by itself, if it was just a normal cubic cell, should have the 1, 0, 0, should have the 0, 1, 0, all of the odds. But because we had a basis, we see that all of the odds got erased from our X-ray scattering pattern. For the BCC, this is what you're gonna get unless you have a basis that cancels things out. Does that make sense? So let's just assume we have a body center cubic with no basis. Then you will have two atoms, one here and one here in this unit cell. If you have a basis, then you have to go through that procedure that I showed you where you take what are the atoms doing, okay? Questions? No questions? All right, so for the cell form factor, we actually have to do, so let's go back over here, where was I? So this cell form factor was the cubic, but it had two atoms inside of it. This one is the body center cubic, but it has two atoms inside of it already. So what we have to do is get this guy for the cell. Depends on G, H, K, L. This is the BCC lattice. And we're going to have some bases on it that depends on G. And then the first atom is just going to give me 1 because it's 0, 0, 0, right? The second atom is going to give me exponential. And here I'm going to have I pi. And then because it's located at HKL, there we go. We close this guy. And then I close the big parenthesis. So it's almost identical to what we had seen before. But these are all the same atoms. They're not cesium and chloride. They're both whatever you want it to be. They're both the same thing. So in this case, we're going to get 0 and twice the F basis. And this is true if H plus K plus L is odd or even. And this is true if HK plus L is even. So it vanishes for some Miller indices if they add up to an odd number. And it vanishes and it is constructive if they're even. And it's the same thing that we did before with the cesium chloride, except that now they're both identical atoms. If you have other one, like for instance, you could do the same thing for the FCC lattice, right? You can look at what if their HKL conditions on them are. And that's pretty easy, right? Because you would be just summing things like that based on the positions of the atoms in your bases. Any questions? Yeah? In this case, yeah, all the even ones are visible. But let's say you had a body center cubic that had another atom in the bases. Okay, so if you have another atom in your bases, then that can destroy some of the patterns that should appear. Any other questions? Yeah.
All right. So for these summations of the Miller indices, are there scenarios where the summation of HK and L being odd and even, or it being odd might cause constructive interference, or is this sort of a universal rule across?
So this would be the rule for body center cubic. There's another rule for FCC, which I'm going to give you guys to figure out on your homework, right? But it's doing the same math, and then you got to figure out what happens. Maybe there's a rule that says that when H plus K is equal to something and L is equal to something else, has some complicated rule, right? I don't know. There's, by symmetry, there's like 250 something things that you can come up with. So I'm sure that there's like super duper complicated rules that are really nice somewhere in there. But I don't look at those things, so that's not my specialty. Somebody like Dr. Myers, he's the in-house expert on X-ray diffraction. He's probably going to tell you all the quirky ones that are super amazing. Yeah. What else? Oh, there was something else that I wanted to just mention to you guys, because this has come up in hexagonal lattices. So we have the hexagonal lattice, that's kind of like where graphene fits in, right? But hexagonal lattice have AB, this is where the graphene planes are, and then you have a C direction. So it turns out that the hexagonal lattice is kind of special because whenever, and this is, it's not really special, it's just a quirky thing that happened. Whenever they came up with the Miller indices for hexagonal lattices, whoever did it first didn't know how to do 3 integers to describe those planes in the hexagonal lattice. So he created a system with 4 planes, with 4 numbers to describe the planes. Does that make sense? So if you look at zinc oxide that has the hexagonal lattice inside of it, the word side lattice, some of those, they actually come out with a 4 index Miller indices, 4 numbers going there. It turns out that those 4, one of them is redundant, and you could have written it like this, but the literature stayed with that first approach that people were taking. And you see, like, for instance, the growth of zinc oxide along the 1, 1, 0, 0, and the 1 bar 1, blah, 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 and then they have 4 numbers in it. That's just quirkiness that happened thanks to people not realizing that they were the same thing as before. So there's a way to go back and forth between them, but we don't need to worry about those things here. All right, You guys have any questions about X-ray scattering at this point? No, we're good. And it is clear that this is different from the other one because this one has two atoms in its bases, right? The other one had two atoms that were different. These are all the same. Okay. So the next thing I wanted to do is talk about let's see. So now we're ready to talk. We have a few techniques already under our belt, but we're also ready to talk about materials. And the most important definition of materials is whether they're metal, semiconductors, or insulators. And that's what I wanted to cover over the next 15 minutes. Let me make sure I don't go over time. Yeah, 15 minutes. And tie this up to what we have covered before already. So metals are defined as a system where the electrical resistivity goes down when you decrease the temperature. So in metals, as T goes down, the resistivity also goes down. At low temperature, the resistivity of the metal is proportional to the square of the temperature and some specific heat that depends on temperature.
How low T are we talking? Just to give us a.
So low T is when you see this behavior.
Right. What I mean is like.
Right. So there's no, I mean, it's metals. It depends on the metal. Some metals, it might be 100 degrees. Some metals, it would be 200 degrees. Some metals, it might be 10 degrees. Depends on the material. But this is definition of a metal. So, so what happens to you is that the electrons in metals are usually, not all the time, described as electrons in a free gas. Sometimes this works extremely well. Sometimes they're described like that and this doesn't apply, but go tell the people who write the papers that they'll get mad at you. So what we know is that this works for metals, and that's how metals behave. And I already told you about some of these things that happened. Like for instance, Bloch started doing this and realized that the electrons were traveling through the metal and they were not hitting anything for long spans of time. And that was because of the periodicity of the metal, right? So it would be like in this particular direction, you can run across this hallway, like this little hallway between the two rows of chairs. That's what he was discovering, that this periodicity in how the chairs were arranged could allow you to run really fast here without hitting the chair. Whereas if you were going in another direction, you would just trip. So that's what Bloch came up with. And he said, oh, this works nice. And we can get that the conductivity is really good and it gets better, right? Conductivity is the opposite of resistivity. And it gets better when the temperature decreases. And that could be seen because the ions are not moving as much. So it's easier. Imagine if you had to run and the chairs were moving around. So that's how electrons behave inside of metals. So There's other people that came up later. They said things that are more more interesting than this idea. And they also came that for the description that Bloch did was just very simple, but it didn't apply to this other collection of materials which are semiconductors. So let me see, do I have the description here? Yeah. So if we have as a function of energy, and the other thing, it could be the wave vector. In this case, is given by K. When you do quantum mechanics, you're thinking like a particle inside of a well and things like that. That's what you learn in our undergraduate quantum, is what you learn in quantum 2, quantum 1. And it's not really applied because that's not how materials behave, right? But it's the toy models that they give you. Electron in a particle well. Then you're gonna have that the well looks a little bit different, but that's never like how matter is. They're not giving you how nuclear matter is, or metals, or semiconductors. Does that make sense? Like, they don't give you a real potential to play with. If you have a collection of nucleons, for instance, you have a potential for the protons inside, and it's not exactly this particle in a well. It's way more complicated than that. One of the reasons that they don't give it to you is because there's no analytical solutions that are easy to do. But with computers, we can solve for all of this. Turns out that for metals or semiconductors, you put the atoms in the right positions, you put them in the structure that they have, and then you would get these really complicated potentials, right? That are not easy to solve by hand analytically, or even with Mathematica or something like that. But they actually can be solved with computers in seconds. It's just that nobody teaches you how to use a computer. So that's actually what we're doing in my group, condensed matter physics, theoretical condensed matter physics group here. We put the electrons, no, not the electrons, the atoms in the right positions, and then try to figure out what is the energy as a function of wave vector. So we have talked about it before. If you have the free electron gas, it looks like this. And free electron gas, it looks like this. For electrons in a solid, it might look like this. And then we have a discontinuity here, and it goes like that. And then this discontinuity can be rotated in this direction, and you would have things that look like this. So we had talked about this where there's a gap right here. A gap in the energy where there were no states when you have periodicity. So this gets treated in your quantum mechanics class. It depends on the instructor, how deep they go into it, but you can solve it for delta functions separated at distance a from each other. So this is the dispersion relationship, free electron gas versus electrons in a lattice. So now if we go and do the systems that we know, and they're not just a lattice that is like a delta function here, another delta function here like this, that would be the simplest one, right? Like you just have these lattice points, individual lattice points. That's what this dispersion relation, the energy as a function of wave vector looks like. If you do it for metals or semiconductor, you could get that maybe this one looks actually like this. And then this one looks like that. Okay? So these two bands, you can see that there's an overlap right here. Do you guys see that there's an overlap? There's electron states are here all the way up to this value. And they continue to here. And then the electron states here are available this K values. So this is bands that overlap. So that's a metal. So that's an example of a metal. If you put the atoms in a particular position. Another example could be one that all of the electron states are filled up to this level. And that field level is called the Fermi energy. And the band continues. So this is a half filled band. You start putting the electrons in there, and you're gonna see that the band doesn't get full. This is also a metal. Questions? So those are metals, that's their band structure. Don't ask me what metals, but I can certainly find in the literature something that looks like this. Questions?
So where the bands overlap in the first place, is that not possible?
You could put the Fermi wavelength there, the Fermi energy here. You could say that that's a Fermi energy. But basically your Fermi energy is that this is the band structure, and then you start filling in how many electrons you have, right? So if you have gold as the ions in there, then you have to put in 79 electrons and you start filling, fill up to here. If you have something up here, and it could be silver, then you have to put 47 electrons and maybe fill up to here. And you have that this region right here is empty, this region right here is occupied. So now, if we are talking about semiconductors, for a semiconductor, we have that here's our wave vector, and here is our energy. And it actually could be that you have something that looks like this. And then here, like that. This is actually what there's 1, 2, 3, 4 bands in this example. Okay, salud. This is actually kind of like a cartoon of what silicon looks like. And in this case, for this system, this is the Fermi energy. And then we see that from here to here, there's an energy gap. You guys see that gap? It's like there's no states between this value and this value. So for semiconductors, we get this. So the definition then goes, what is a semiconductor? In semiconductors, we get an energy band gap. And this energy band gap, there's no real accepted definition of what. So here's the thing. If your band gap is 10 electron volts, you have an insulator. If your band gap is smaller than maybe 3.5 electron volts, you have a semiconductor. If the band gap is very tiny, then when you're at low temperature, it's kind of like a semiconductor. But if KBT is bigger than your band gap at that temperature, you start seeing that it behaves like a metal. So if KBT is close to the band gap, your semiconductor behaves kind of like a metal. And KB is the Boltzmann constant times the temperature, right? KBT. If this is between 1 and 3 electron volts, then you have a semiconductor. And it's not set in stone, like I said. So in semiconductors, if it's bigger than that, then you have if you have something bigger than the 3.5 electron volts, they're called wide bandgap semiconductors. Somebody could present on what those systems are useful for. If you have something that has a bandgap of about 6, I would call that an insulator. Some people might say it has to be bigger because that's wide bandgap. Doesn't matter, right? It's just words. The important thing is that it's harder for them to conduct if the bandgap is really big. All right, so this would be obtained for putting the silicon structure in a phase center cubic with a basis of another phase center cubic inside of it. So that's your phase center cubic with a basis that is half another atom in it, gives you this. If you make those atoms be silicon, you can calculate that structure. This is the energy versus wave vector that pops up. And you can measure what this energy bandgap is, where you have that. We could look at another one, wave vector versus energy. In this case, we're gonna have that there's something that is gonna look like this. So this one is really nice because it looks like this, and then it looks like this. This one is for germanium. Actually, assume that this is perfectly symmetric like that. So here at the same wave vector, you have this is the top of this band. Right here, this is the top of this band, and this is the bottom of this band. Then your Fermi wavelength is, your Fermi energy is in between those two values right there. And the band gap is close enough to, this band gap is here, and this is about less than 2 electron volts too. So this is the best looking semiconductor, germanium. So just a closing remark about semiconductors. Pauli gave us some really good advice. He said one should not work on semiconductors. That is a filthy mess. Who knows whether any semiconductors even exist? So this is Pauli, right? Like one of the great physicists. So that was his advice. He didn't like semiconductors. He also thought that all of this physics was boring because he was just putting them into a Hamiltonian that was easy to solve with computers. But it turns out that obviously he was wrong because semiconductors have been probably the most important development for all of technology in the last 90 years. We have all of these cool things, right? These guys, because of semiconductors. If you only had metals, life would be boring. All right, so that's where I want to close today. I need somebody else to sign up for materials, at least. And then techniques is going to be, we'll continue with materials and techniques when we come back from break. All right. So I'll see you guys on Thursday. And if you have questions about what you want to present, just let me know and we can work it out, whether it's a good idea or not.